Okay, here goes. The base 10 number system. The base 10 number system is what we use day to day. This is the normal system of numbers that we use. And what we're going to do is we're going to look at the base 10 system to begin with, and that's going to set us up to look at clock and modular arithmetic. And then looking at down the road a bit, clock and modular arithmetic is going to set us up for working in bases that aren't base 10. But for now, let's just talk about the base 10 system. The base 10 system has the following digits in it. If I'm just going to write one single number down, the digits are 1 through 9 and 0. So it's a base 10 system. There are 10 different digits, 1 through 9 and 10 and 0. Notice here, in the base 10 system, the largest digit is 9. So if we're in the base 10 system, the largest digit that we have is 9. The biggest number we could write in one single place value position is the number 9. Why is this called the base 10 system? Well, if we look at our place value positions in the base 10 system, we've got our decimal point here, and we have the ones place. Next to that, we have the tens place. Next to that, we have the hundreds place. And next to that, we have the thousands place. Let's think about those numbers for a minute. You may not remember your exponents from algebra that well, but something that's true, when we raise anything to the 0 power, the answer is 1. What I mean by that is if we say 3 to the 0 power, raised to the 0 power, it's 1. If I have 7 raised to the 0 power, that's 1. Anything raised to the 0 power is 1. And so this first place value position that we have here, that's 10 raised to the 0 power. That's the ones place. This will fall into place for you a lot better as we keep moving to the left here. 10 raised to the first power. Well, that's just 10. That's the tens place. Moving to the left. 10 raised to the second power is 100. That's the hundreds place. Continuing to move to the left, 10 raised to the third power is 1,000, and that's a thousands place. And this keeps going to the left. We have ones, tens, hundreds, and thousands because we're in a base 10 system. And in a base 10 system, 10 to the 0, then 10 to the first, 10 to the second, 10 to the third tell us what our place value positions are going to be. You may remember that when we have something written like 10 to the second power, this thing is called an exponent. And this thing down here is called the base. And so when we look at ones, tens, hundreds, thousands, that's a base 10 system because every base in there is 10. And so that's our base 10 system that we use all the time. Just sort of have that in mind as we move forward throughout the next couple of days. Let me know if you have any questions about anything that's on there that we talked about right here with base 10. Outstanding. All right. Expanded form. This is a term used in our book, and I want to make sure that when you see expanded form, you know what it means. If we take the number 527, and we're told to write this in expanded form, here's what that means. We start out by saying, well, that's 500 plus 20 plus 7. So I've expanded it a little there by saying that 527 is 500 plus 20 plus 7. And then we could go a little more here and say, well, this is 5 times 100 plus 2 times 10 plus 7 times 1. What we've done in this step is we've incorporated our place value positions into our number. We have ones, tens, and hundreds. And for this particular number, we have 5 hundreds, 2 tens, and 7 ones. That's what the number 527 is. If you're thinking this all feels pretty obvious, that's okay. As we get deeper and deeper into numeration, having this really simple idea at the beginning is going to be really good for us. And then we can even go one step further than this, and this is how we're going to finish off expanded form. Instead of 100, I'm going to write that as 10 to the second power. Instead of 10, I'm going to write it as 10 to the first power. And then instead of 1, I'm going to write it as 10 to the 0 power. And here again, we're emphasizing those place value positions and where they come from. The 1's place is 10 to the 0, the 10's place is 10 to the first, and the 100's place is 10 to the second. And so writing the number 527 in expanded form means writing it this way, as 5 times 10 squared plus 2 times 10 to the first plus 7 times 10 to the 0. That's what expanded form means when you see that term in your book. Let me know if you have any questions on anything that we did there. Okay, very good. More about base 10. If we just throw a question out there, how many 10s are in 370? How many? And yeah, Laura, you can type this in. Anybody can type this in. How many 10s are in 370? Let me make sure this question is phrased correctly. There is a 7 in the 10s place, but if I just want the number 370, how many 10s would it take to make this number? There we go. There we go. So maybe it's the phrasing of this question that wasn't great. This is the phrasing that our book's going to use for a question that's similar to this. How many 10s does it take to make 370? And so instead of just what number is in the 10s place, it's how many 10s does it take to make this number is what this question means. And Stephen, Austin, Katrina, you've got it there, 37. And there's a couple different ways you can get to this answer. One way that I'm kind of hopeful for is you look at it and say, well, if I look at where the 10s place is, there's 37. It would take 37 10s to get there. Another way is a little more mechanical and shows a little less understanding, but you could get the right answer this way and just say, well, if I do 370 divided by 10, that'll tell me how many 10s it takes. This is okay. This will get you the right answer. But the way I want you to approach this is say, well, here's where the 10s place goes. So there's 37 of them. I'm going to have you try one that's similar. I'll make a poll for this one, so don't type it in. How many hundreds are in 31,000? So what we're getting used to here with our sort of introduction to base 10 and reminders about base 10 is what our place value positions are, where our place value positions are, and what they represent. So if you're kind of thinking, this is awfully simple, yeah, it is. We're just setting up base 10. Later on when we work in other bases, this knowledge that we're kind of brushing up on right now will be really valuable for us. Let's go another 15 seconds and then we'll do this one together. All right, let's see what we've got here. Strong agreement, not unanimous. That's kind of typically where we land. If when we talk through this, if you have any questions, if it doesn't get cleared up for you, make sure you ask about that. I don't want you to go away feeling like you didn't really get the idea of this. So how many hundreds are in this number? How many hundreds would it take to make that number? And one way to approach this is to say, well, let me do it this way. This is where the hundreds place is located. So what do I have over here? I have 310 hundreds. If we look at it from that standpoint, we have 310 hundreds. Kind of a strange question. It's not a normal question for us to answer, but hopefully it makes sense. And then obviously you could do 31,000 divided by 100 to find out that sure enough, that's 310. But visually, looking where the hundreds place is located, it takes 310 hundreds to make 31,000. Does anybody have any questions about the base 10 stuff that we've talked about? Mostly that's a reminder, refresher of some things that you're probably aware of, but don't really spend much time thinking about before we get into other bases later on. All right, now we'll get into the topic of the day, which is clock and mod arithmetic, and we're going to start with clock arithmetic. And so my question to you is, if it's 10 a.m. now, what time will it be in 4 hours? And you can type that one in. I'm not going to make a poll or anything. If it's 10 a.m. now, then what time will it be in 4 hours? 2 o'clock, 2 p.m., 2 o'clock, 2 o'clock, 2 p.m. Very good. Laura, Denise, Kate, Katrina, Ariana. Perfect. That's okay. That's okay, Laura. I gotcha. And that's exactly right. If we look at this clock, if it's 10 a.m. now, then in 4 hours, we just go 1, 2, 3, 4, then it's going to be 2 p.m. So what we just did there is said that 10 plus 4 equals 2. I mean, we're all pretty comfortable with the idea that if it's 10 o'clock now, in 4 hours it's 2 o'clock, but we just said 10 plus 4 equals 2. That's pretty weird. That's not something we would typically write down, 10 plus 4 equals 2. Well, if we're on a clock with 12 hours on it, sure enough, 10 plus 4 does equal 2. Because this number system that we have over here, it only goes from 1 to 12. That's it. There's nothing bigger than 12. Nothing smaller than 1. That's it. That's the whole number system. So if we do 10 plus 4, we get 2. That's the idea of clock arithmetic. One of the ways you can do this that a lot of people really like is with a picture. I'm at 10. If I go forward 1, 2, 3, 4 hours, now I'm at 2. Okay, what if I want to do some clock arithmetic like 7 plus 6 on an 8 clock? Well, the first thing I've got to do is get in my head, what the heck is an 8 clock? Well, the normal clock we deal with, we could call it a 12 clock because it goes from 1 to 12. If we have an 8 clock, then that means it goes from 1 to 8. So, and you're drawing here, if you're going to use a picture, which I think is a great way to go, your drawing doesn't have to be perfect. We'll just have 1, 2, 3, 4, 5, 6, 7, 8. There's my 8 clock. And if I want to do 7 plus 6 on this 8 clock, 7 plus 6, I'm going to start here at 7, and I'm going to go forward 6 from there. 1, 2, 3, 4, 5, 6. And I end up at 5. So 7 plus 6 on an 8 clock is 5. Clock arithmetic means we're restricted with the numbers we are allowed to use. When I start at 7 and I go to the right 6, because I'm adding, we can also subtract on here, but if I'm adding, I go to the right, and 6 hours later, it would be 5 on this 8 clock. Another way to approach this that some students really like is 7 plus 6. Well, I know 7 plus 6 is 13. Problem is, I don't have a 13 on my 8 clock. So 13 can't be the answer. 13 doesn't exist. 7 plus 6 is 13. So 13 is no good, but if I'm sitting here at 13 and I do one whole revolution backwards, then I'll see where I'll be. If I do one whole revolution. So let's see. Oh, I also want to do this. 7 plus 6 is 13. You could just start counting and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You still end up at 5. If you do it just by writing it down instead of using a picture and you're at 13, we need to do one revolution backwards. What we're going to do is an entire revolution would be 8, so we'll subtract 8. That's one entire revolution. That's going to put me right back where I was before. Now I get 5. 5 is a number that I'm allowed to have for an answer, so 5 is okay here. Yeah, Denise, you're exactly right. We're subtracting 8. Perfect. I didn't catch that early enough, but you're exactly right. We subtract 8 because we're going one revolution backwards on an 8 clock. If we were on a 12 clock, we'd have to subtract 12 to go one revolution backwards. Let me know if that doesn't make sense. Any of these approaches are completely fine. You can do this by just draw a picture, start at 7 and count forward 6. You could do it by adding these up to 13. Count all the way around till you get to 13. Or you could do 7 plus 6 and then subtract 8 to make sure you get a number that's allowed. Because we know on an 8 clock, our answer has to be 1, 2, 3, 4, 5, 6, 7, or 8. Can't be anything else. So 13 is no good here, but we can do a revolution backwards and land at 5. All right, let's have you try one. I want you to do 6 plus 5 on a 7 clock. I'll make a poll for this. These are probably new for most of you, but I hope that you see them as kind of fun. The big picture, what we're doing here is getting ourselves used to working in something that's not your standard 1 through 10, not your standard base 10 system. That's why we're going to do clock and modular arithmetic. They're kind of cool and they're kind of fun, and they set us up for working in systems that aren't base 10. We'll go another 15 seconds, and then we'll talk through it. All right, let's see how this one went. Strong agreement, not unanimous. That's all right. If you have any questions about what we're doing when we go through it, make sure you ask those questions. So here we're doing 6 plus 5 on a 7 clock. There's a couple of different ways you can go here. You can draw yourself a 7 clock. Doesn't have to be a work of art. And we want to do 6 plus 5. So you could start at 6 and go 1, 2, 3, 4, 5, end up at 4 and say that's my answer. Perfectly fine, nothing wrong with that. You could instead say, well, 6 plus 5 is 11. So what if I just start at the beginning of this clock and go around 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Still landed at 4, so that works. The way that most of you will probably like the best once you get comfortable is doing it with arithmetic and saying 6 plus 5 is 11. 11 could be an answer. The problem is, because I'm working on a 7 clock here, I don't have an 11. So wherever I am, I need to do one full revolution backwards. I need to take 7 away, end up at 4, and that's our answer. So you can do this by drawing a picture or by doing arithmetic, whichever way makes you comfortable. Let's try subtraction. 4 minus 7 on an 8 clock. I'll make a poll for this one too. Subtraction's a little bit different, but the philosophy doesn't change. You can do it with a picture. You can do it with arithmetic. Just be careful with the arithmetic and remember you're on an 8 clock. We'll go another 15 seconds and then talk through this one. If you need more time, let me know. If you get an answer that's not there, pick the one that's closest to yours. All right, let's see what we've got here. Okay, again with strong agreement. If you're able to solve these correctly, that's fantastic. You're in a really good place. If you're just not seeing it, make sure you ask for help. 4 minus 7 on an 8 clock. You can absolutely do this by drawing a picture. So there's an 8 clock, and you could start at 4 and go backwards 7. Now we want to go counterclockwise. We want to go to the left on our clock because we're subtracting. 1, 2, 3, 4, 5, 6, 7. We end up at 5. So by drawing a picture, we can see our answer is 5. Perfectly fine. Perfectly good way to go. You could also do 4 minus 7. Well, that's negative 3. The problem is my clock does not have any negative numbers on it, so that can't be the correct answer here. Now, because I'm in the negatives, I need to make a full revolution going forward. So I need to add 8 to that, and I'll end up at 5, and sure enough, that's our answer. Whether you do it by drawing a picture or just doing arithmetic, we want to make sure our answer is on our clock, and so we needed to do a full revolution forward to get there, and that was 5. Let me know if you have any questions on that. I get a sense this is going really well, which is exactly what I hoped and expected. Okay. This one's harder to do by drawing a picture. 5 times 4 on a 6 clock. You can do it by drawing a picture. I'm going to go ahead and make a poll for this one too. We'll go another 20 seconds and then talk about this one together. Harder to do a picture with multiplication. It's not impossible because it's 5 times 4. You could just do 5 4 times or 4 5 times as you go around your clock. We'll do this one in reverse order. We'll do this one first by doing the numbers, and then afterwards we'll do it with the clock. All right, let's see how we did here. Agreement, but a little more disagreement on this one. So this one was tougher, which I kind of expected because of the multiplication. So let's take a look here. So 5 times 4 on a 6 clock. What most of you probably did was, well, 5 times 4 is 20. But if I imagine myself having a 6 clock over here, that's 1, 2, 3, 4, 5, 6. Those are the only possible answers. 1, 2, 3, 4, 5, 6. Nothing else can possibly be my answer here. So 20 is no good. So I need to do an entire revolution backwards. So I'll subtract 6, and that puts me at 14. Well, 14 is in the same place as 20. The problem is 14 is not on my clock either. My clock only has 1, 2, 3, 4, 5, and 6 on it. So the answer can't be 14. So I'm going to have to subtract 6 again. That gets me to 8. And 8 would also be in the same place. The problem is my clock only has 1, 2, 3, 4, 5, and 6 on it. So 8 is no good. So I'm going to have to subtract 6 again and get 2. Now 2 is on my clock. And so 2 is going to be our answer here. 5 times 4 on a 6 clock is going to be 2. And it's because 14 is not on our clock, 8's not on our clock, so we have to go all the way to 2. If you did this on the clock, 5 times 4, so I'll do 5 4 times. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Sure enough, I end up at 2. Just to sort of show you that 20, 14, 8, and 2 are all in the same place, if we were to count to 20 from the very beginning, we'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20. 20 would be in the same place. If we went to 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, same place. And then 1, 2, 3, 4, 5, 6, 7, 8, same place. All those are in the same place. The only one that's actually on our clock, though, is 2. And so that's why our answer here has to be 2. No, that's it, Madison. That's it exactly. Keep subtracting 1 full revolution until you get a number that can be your answer. And it's important to note the reason we subtracted 6 every time is because we're on a 6 clock. Here's a question very similar to what we just did. Find the equivalent of 37 on an 8 clock. So what we're doing now is we're not going to add, subtract, or multiply. We're just going to say what would be in the same place as 37 if we were on an 8 clock. Certainly, you can do this by drawing an 8 clock and counting around to 37 and see where you're at. That's perfectly fine. Another way to go here is to say, well, I'm at 37. If I subtract 8, I'm at 29. If I subtract 8 again, I'm at 21. If I subtract 8 again, I'm at 13. I'm getting there, not quite there yet. But if I subtract 8 again, I'm at 5. And so the equivalent of 37 on an 8 clock would be 5. Anybody have another way to go about this? It's very similar to the problems we had where if we have the word Czechoslovakia and we want the 270th number, how would we do that? You can also approach a problem like this the way we approached that problem. So if I said, I'm just going to do 37 divided by 8 here and see what I get. So if I do 37 divided by 8, I get 4.625. I'm going to throw away this decimal part. I'm not going to concern myself with that at all. What this tells me is if I'm going to go all the way to the number 37, I'm going to have to do 4 complete revolutions. When I do 4 complete revolutions, that puts me at 32. And then I need to go 1, 2, 3, 4, 5 more. And so it's the remainder when we do this. It's very similar to those when we had the word like hip hip hooray or mathematics or Czechoslovakia, and we need to find what's in the 230th position. What we're finding out here is what would be in the 37th position. You can do it any one of these 3 ways. You can draw a picture and count around to 37. You can start at 37 and subtract a full revolution until you get to a number that's actually on the clock. Or you can divide, throw out this part, and realize, well, 4 times 8. So I'm doing 4 complete revolutions. That's 32. And so to get over to 37, I need to go 5 more. Any of those ways will work for a problem like this. Let me know if you have any questions on that. Outstanding. All right. So we did some base 10 review just to sort of set ourselves up for number systems. Then we've done clock arithmetic. Up next, we're going to look at modular arithmetic. A modular system is just a group of numbers, and modular arithmetic is almost exactly the same as clock arithmetic, except there's one major difference. When we're on a clock, we don't have 0. Clocks don't have 0 on them, but modular systems do. What I mean by that is, if we're in a mod 5 system, it's going to consist of 5 numbers. And those digits are going to be 0, 1, 2, 3, and 4. Notice, if we're in a mod 5 system, the largest digit is 4. We don't have 5 in the mod 5 system. The largest digit we have is 4. We have 0, 1, 2, 3, 4. There's 5 digits. The largest is 4. This is exactly parallels our base 10 system, just to sort of show that parallel. In a base 10 system, we have 10 digits. We have 1 through 9 and 0. I should probably write it the same way I did these others. We have 0 and 1 through 9. The largest digit is 9. The largest single individual digit in our base 10 system is 9. When we're working in a mod system, it's very much like our base 10 system in that mod 5 means there's 5 digits. These are those digits, and the largest digit is a 4. If we were going to draw a picture of a mod 5 system, it's going to look very much like our clocks from before. It's just now we're going to have 0, 1, 2, 3, 4. That would be a picture of a mod 5 system. We're going to do the same kind of arithmetic, add, subtract, multiply, find the equivalent of with a mod system that we did with clock arithmetic. The only way that modular arithmetic is different from clock arithmetic is the inclusion of 0. That's right. That's right, Joanne. Clock arithmetic doesn't have a 0. There's no zeros on the clocks. If we go back and look at the problems we did, when we did an 8 clock, there's no 0, just 1 through 8. And when we did a 6 clock, there's no 0, just 1 through 6. And so now that we're in the mod system, we do have 0. All right, let's look at one of these. So I want you to try it. 3 plus 4 in the mod 5 system. So using mod 5, find 3 plus 4. I'll make a poll for this. Your approach is the same as it was with clock arithmetic. You can do this by drawing a mod 5 system and counting around the circle. Or you can do it with arithmetic. Just make sure that the answer you get is a number that is actually part of the mod 5 system. We'll go another 15 seconds, and then we'll talk through this one. All right, let's see how we did. Okay, strong agreement, very strong agreement, not quite unanimous. If you see anything in here that you're unsure of or you want to ask about, make sure you do. So as we look at this, 3 plus 4 mod 5. You can absolutely draw a mod 5 system if you want to. Remember, a mod system has 0, and if it's mod 5, the biggest number is 4. There's no 5 in here, so don't put one. 5 digits, largest one is 4. There's our mod 5 system. If I want to do 3 plus 4, I could start here at 3, and I could go 1, 2, 3, 4, and end up at 2. Or what most of you probably did was 3 plus 4 is 7, but there's no 7 on here. To do a trip around this backwards, even though the largest digit is 4, one full trip around here is there's 1, 2, 3, 4, 5 digits. So if I want to do a full trip around, I need to subtract 5 from this to end up at 2. And so my answer would be 3 plus 4 in a mod 5 system is 2. Kind of weird to put 3 plus 4 equals 2. We wouldn't really ever write it like that. Really what we would write is 3 plus 4 mod 5 is 2. Your answer when you give it on a quiz or an exam is just going to be the 2 because the question's going to include mod 5 in it. So it's going to be understood that we're working in a mod 5 system. 5 minus 7, mod 9. I'll make a poll for this and we'll see how it goes. So far, polls have gone really well, which is great. Same philosophy as clock arithmetic. The only difference here is now we have a 0, and this system won't have a 9 in it. And my advice to you here is if the arithmetic way works well for you, then just keep doing that. If the arithmetic way is not working for you, draw a picture and actually count. It may be a little more work, but it's not a lot. And the most important thing is getting it correct. And if using the actual physical clock to get to the answer is what works for you, then do that. Let's go another 15 seconds and then we'll do this one together. All right, let's see how we did here. Yeah, we have agreement, but we're spread around a little on this one. So, all right, let's talk through this one and make sure you ask if you're not sure how yours arrived at a different answer than what we get. 5 minus 7 mod 9. If you were to draw a picture of this, it's mod 9, so the biggest number is 8, and there's, oops, I need a 0, 1, 2, 3, 4, 5, 6, 7. So kind of clumsy, doesn't have to be a work of art, but there's my mod 9 system. I have 9 numbers, 1 through 8 and 0. If we're 5 minus 7, and I do it over here on this diagram, I start here at 5, and I need, because I'm subtracting, I'm going to go backwards. 1, 2, 3, 4, 5, 6, 7. So I've ended up at 7. So we know 7 is going to be our answer. What most of you probably did was 5 minus 7 and got negative 2. Well, while it's true, 5 minus 7 is negative 2, negative 2 is not one of the numbers in my system. Since I'm in the negatives, I don't want to subtract here. I don't want to subtract 9 and go negative 11. That's just going to make it worse. What I'm trying to do is get a number that's actually in my system. Since I'm in the negatives, I'm going to need to add 9. One trip around, go in the positive direction. When I do that, I land at 7. And sure enough, that's 5 minus 7, mod 9, would be 7. Let me know if you have any questions about how we got that 7. The key here is, if we get a number that's too big to be in our system, we need to subtract till we get something that is. If we get something that's too small to be in our system, we need to add till we get to something that is. And one trip around, and you subtract the negatives from the mod. I'm not sure I know what that means, Austin. Try to phrase that again. We'll see if we can suss it out. Oh, sure, sure. Yeah, 5 minus 7 would be negative 2. If it was mod 10, we'd add 10 and it would be 8. Yeah. So you good? All right. If that didn't fix it, you let me know. But yeah, it works in mod 10. Now, one thing that wouldn't make sense, just as a little aside here, is if we tried to do 5 minus 7 mod 4. And the reason that's no good is because 7 doesn't exist in mod 4. So this we wouldn't be able to do. But 5 minus 7 in mod 10, totally fine. Multiplication, 4 times 3, mod 6. I'll make a poll for this one too. These are going really well across the board, but if anybody has questions that you want to ask about how we're getting these answers, definitely ask those. If you have questions like Austin's, it's like, yeah, but what about this thing here? Make sure you ask those too. I think this is a really fun topic. And so if you have something that you want to throw out there, don't hesitate to do it. The multiplication was the toughest one last time. It's probably the toughest one here too, but the idea is the same. We're just doing 4 times 3, but we need our answer to be in the mod 6 system. Let's take 20 more seconds and then talk about it. If you need more time, let me know. If your answer is not there, pick the one that's closest. right, let's see how this one went. Again, strong agreement. That's good. The mistake here is an easy one to correct, though. I think we'll be fine on this one. So as I look at this one, and we'll do it without the picture first. We'll add the picture in after. So if I want to do 4 times 3, 4 times 3 is certainly going to be 12. Problem is, in a mod 6 system, that only has 0, 1, 2, 3, 4, and 5 in it. It doesn't have 12. So I can't have 12 as an answer. So imagining myself going backwards around that circle, one whole trip around backwards, I need to subtract 6, which puts me at 6. And kind of feels like 6 ought to be in mod 6, but wait a minute. Mod 6 does not have a 6 in it. Mod 6 is 0, 1, 2, 3, 4, 5. There's no 6 in there. So I can't have 6 as an answer because 6 doesn't exist in this system. So I need to do another revolution backwards, so I land at 0 as my answer. A mod system does have a 0. Clock system doesn't. So it's possible when we're doing modular arithmetic to get an answer of 0. So mod 6 system is 0, 1, 2, 3, 4, 5. If I did 4 times 3, which I could say, well, that's 12. I'll just count around 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm at 0. Or if you wanted to do 4 times 3. So I'll do 4 3 times. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Sure enough, no matter how I get there, I get to 0. Oh, well, if you're counting anything, that's not a silly question at all, Laura. It's a good question. If you're counting anything, you would start at 1. The first thing you would count would be 1, whether it's jelly beans or how many kids are in a classroom. Your first thing you count would be 1. But it's an excellent question, though. So yeah, we'd start out by going 1, 2, 3, 4, 5. Good question, though, actually. Yeah, so we always start counting at the 1. And that was true in our clock problems also. Find the equivalent of 29 mod 5. I'll make a poll for this one too. So we've done addition, subtraction, multiplication, and now we'll do find the equivalent of. So what's the same thing as 29 if we're in a mod 5 system? Do another 20 seconds. Need more time, let me know. All right, let's Let's see how we did on this one. Hey, unanimous. Fantastic. Hey, if one of them was going to be unanimous, the last one we're doing being unanimous is really good. So a couple of ways you could go about this. You could absolutely draw a picture of a mod 5 system. Mod 5 is going to be just 0, 1, 2, 3, 4. 5 numbers, it does include a 0. And you could count around until you got to 29. That would be just fine. What most of you probably did was 29. Oh, another way you could go, sorry about that, is 29 is no good, but I could subtract 5 and get 24, and I could subtract 5 again and get 19, and subtract 5 again and get 14, and subtract 5 again and get 9, 2, and subtract 5 again and get 4. Finally, got there. Probably a little clumsy for most of you. The most common approach was probably if I do 29 divided by 5, I get 5 point something. I don't care about the something, but what I get from this is 5 times 5. That's going to be 25. So I'm just going to make 5 complete revolutions around this thing and be right back where I started. And then in order to get to 29, I need to go 4 more. And if you want to see that written down, you could 29 minus 25 means I need 4 more to go. And that's how I'll end up at 4. I'm going to do 5 complete revolutions and then go 1, 2, 3, 4 more to end up at 4. So what's the equivalent of 29 mod 5? 4 is, depending on which way you wanted to go about that. I really like